everybody. Today I'm going to be helping you to understand how aircrafts fly upwards and how they could be resisted to move, which is lift and drag. It's the basics of aerodynamics. And so first of all, we need to talk about lift. So what lift is, it's actually the force that keeps an airplane or aircraft go upwards. We have four forces, and I think you should already know them, which you have the weight, which is the weight of the aircraft going downwards. You get the thrust, the force that makes the aircraft move forwards, and then you get the lift that goes up, which is the whole point, airplane flying in the sky, which makes it go to the sky in the first place. And then you get the drag, which is the resistive force slowing down the airplane, opposite to the thrust. Okay, now first of all, the lift. Now how lift happens, actually there is three ways to explain it, but first of all we need to understand how it's explained using pressure, which is kind of like Bernoulli's theory. So the pressure on top of a wing, as you see on the right side of the video here, in the blue, it's like an airfoil. Airfoil is just a cross section of a wing. Okay, so yeah, you get airflow upwards. You see these three arrows going in straight line, and then you get two arrows going in straight line under it. The airflow upwards, okay, so there is less pressure on the top of the wing than on the bottom of the wing, which causes the lift. Okay, and then we'll talk about it more in detail soon. So then we have to explain now what the equation for lift is. So lift is a force, and we calculate the force, the lift force, using this equation here on the left side, which is the surface area of the wing multiplied by the coefficient of lift. So, and then multiply it by half, and then rho, and then c squared. C is the velocity of the air. Okay, so it's not the velocity of the airplane, no, it's the velocity of the air that is going past it. Okay, and now the lift coefficient, I've touched a bit on it, which is how good the wing is, and it's dependent on so many factors. One of them is the shape. Okay, the shape of the wing, and we'll get to that in other videos. Okay, now we have talked about pressure, but how does that happen? How do you have less pressure on the top? That is because the airflow on top of the wing is much faster than the airflow on the bottom of the wing. Therefore, you have lower pressure on the top than the lower, okay, bottom, which causes lift. But there's some questions here. How does the flow join back together? You see, like the arrows, how do they get back together? That's another story. Okay, now there are some things we have to talk about. So first of all, you have like a plate. Okay, so this plate goes like this. It's angled, you can see. Okay, and we are letting it to move quickly, okay, through the air. So, and it rises. That's how airplanes take off, right? So this is an airplane. It angles up, and then it goes pew. Okay, so what happens is, as the plate is moving forwards very quickly, right, there is like this stream of fluid goes downwards. Okay, so this goes like this, and then there is airflow going downwards like that of the back edge. So the back edge is here, sorry, here. Okay, that's the back edge. So you get pew, and then here, and because it's going downwards, the airflow, as you see here, the arrow is going down backwards. Now, Newton's third law says for every action there is an equal and opposite reaction. What happens here is that the plate is pushed upwards, okay, because of the reaction force. Now, we have some things where, like, what happens when the flow is sent downwards? It could happen, okay? So when you move an airfoil, again, to remind you, an airfoil is the cross-section of a wing, okay? So you cut a wing, let me show you here. This is an airplane, okay? This is the wing. You cut it through here, you get a cross-section, okay? You get infinite cross-sections. Let me make it more clear here. You see, this is a wing. And then that cross-section is called an airfoil, okay? So when you are moving an airfoil through the air, okay, so there will be some flow going downwards. Yes, just like the previous example I told you, the plate, but this time the plate is the airfoil. So because of that, the airfoil's curved shape exists to minimize drag. That's why an airfoil is curved, okay? So we don't want the drag to form from the flow separation, because flow separated, okay? So this causes lower drag, okay? Now, there is something called vortices. As you see these circular arrows. We're going to be talking about them more. And when you have flow separation and vortices, they can cause high drag. Okay. Now, when we want to talk about vortices, we should not forget about the Magnus effect. Okay. Now, the thing with the Magnus effect is that it is it's like what happens when you have vortices. So think about, have you seen a picture of an airplane that is like a picture of it going, and then you get vortices like these weird smoke? You could search it up and then you will find out, okay? So when you have like a spinning object in a flow, so it tends to move perpendicular to that flow, okay? So you see here we've got an object, that one, that's straight, and because it's going in a spinning object, yeah, so you will have vertices, okay? So if you pull a flat sheet through a fluid and a series of vortices comes off it, okay, that's just something that would happen. So what would happen if you have more vortices on the top than underneath? What happens is that it takes energy to create the vortex, okay? Every vortex, you have to have so much energy on the top of the wing to make it. When you use all of that energy on top of the wing to make these vortices, that there is no more energy for the pressure to exist, so all that pressure is dissipated on the top, which causes the lower pressure on the top of the wing than the lower, okay? So it all like links up. So that's why then you got lift produced. There is a side effect though. The imbalance also tends to make the wing climb. So then when I say the wing climb, the angle increases. So if this is the wing, the angle increases when you got that type of vortices. So vortices are only good when the vortices on top of the wing is much higher than on the bottom. Now, just to look at it in a more complete picture, we've talked about three things that can cause lift. So we talked about Bernoulli's, which is the flow on top of the wing is much faster than the bottom, causing lower pressure. And the second reason there's lower pressure on the top is because you got more vortices on the top. And then we also talked about, remember when we talked about the plate and how we put in the Newton's third law, as you got airflow downwards the trailing edge. So if we combine all of that together, we get lift. Now we have to talk about drag. So drag is not opposite of lift, no. Drag is the opposite of thrust. Many people always mistake it for the opposite of lift for some reason, but no. When you have an airplane, okay, that's the thrust if it's moving that way. That's the drag, that is resistive force, okay? So we got three types of drag. We got form drag, which happens because of the shape of the object, or like, let's say, aircraft. Think about Formula One cars. They're very streamlined, and that's for a reason. The reason for that is so it has less drag, so it moves faster, okay? And this is because air is, so if you have like a less aerodynamic object that's not streamlined, it's just like bulky from the front, air is slowed in the front and pushed backwards, causing more resistive force. Now friction drag is just in the name. You have the object, you've got the molecules on the object, they rub with the airflow, air molecules, causing friction, and then therefore slow down. You got induced drag, which sounds pretty weird because it happens because of the lift itself. So the energy needed to deflect the flow and create lift creates drag itself, okay? Now we want to look at the formula for drag again. Force equals, so it's the same as lift, but the only thing that we changed is that A is not the area of the surface area of the wing, is actually frontal area, okay? And then the drag, so the coefficient is actually coefficient of drag, okay? Coefficient of drag describes like it involves like how streamlined the object is, okay? So here let's talk about form drag, okay? So we've got versus streamlined shape. Now here on the left you got a bluff body, so it's just a complete rectangle. It's not streamlined, as you see, and then the momentum is exchanged to the body in front, pushing it backwards. Also think about it, turning effect is always momentum, okay? And low pressure behind sucks it backwards, okay? So skin friction, okay, drag is like, again, we talked about the molecules, this is just to sum it up more. Now induced drag, this is a bit tough to understand, but what it is that so creating lift, okay, means deflecting the airflow, and we have explained how that works, right? And sorry, the energy to do that has to come from somewhere, right? So you want lift to happen, and for that to happen there must be some energy, okay? It comes from the flow itself, the airflow. That's what happens, that's the only energy we're bringing it from. And overcoming the loss is what causes the induced drag, okay? There is lower energy so because there is thrust, some of the energy from the thrust is used, it creates airflow, higher airflow, which is used for lift. Think about it this way. An aircraft does not fly by itself. It needs an engine. It needs thrust. When there is thrust, and it's angled up, then it flies, okay? So some of that energy from the thrust goes to help the lift, which means the thrust force is not completely used. Some of it is used, so there's drag, okay? Now we have something called stall, okay? Now there's something called an angle of attack. Angle of attack, remember the airfoil, okay? So let's say this is an airfoil which is angled upwards. It is the angle from here. That's the angle of attack, how angled up, okay, the airfoil is. And the thing is, the higher the angle, right, of attack, the higher the coefficient of lift. We are going to talk more about how that actually works, okay? So if the coefficient of lift increases, obviously the lift itself increases because of the equation of the formula. But here is the thing. It can reach to a point, as you see on the graph on the left side, where actually it does the opposite effect. As the angle of attack increases after an optimum angle, the angle, lift coefficient decreases. Okay, now which is called stall. Okay, so stall is the point where the lift coefficient decreases at some point on the angle of attack. Okay, so we also have how the drag coefficient works, and this is the thing. So the more the angle of attack, the higher the drag coefficient, and it kind of increases in an exponential way. No, I wouldn't say so, but if you look at it from like a big, huge data, that's what it would look like. So you have to know some units, how they work. This is very simple. You should be able to know them already, but I just want to talk about it. So density, which is rho. You could just read the table if you want, but there's a couple of things I want to emphasize. Mass flow rate, which is written as m dot, is just the mass divided by time, and in the other videos you'll find out why we use it. Velocity, yeah, we don't need to talk about that. Volumetric flow rate is v dot, just the same as m dot, except we're using velocity divided by time. And temperature, you need to use Kelvin, okay? Now, when it comes to pressure, okay, this is very important. You got something called the absolute pressure, right? Which is the sum of two pressure. Ambient pressure is the atmospheric pressure, okay? So the pressure dependent on the atmosphere. Gauge pressure is the pressure that is increased from an object, okay? And if you want to find the absolute pressure on an object, you have to combine both of the pressures. Now, one bar, okay, this is very important. 1 bar equals 10 to the 5 newtons or pascals. Let's use pascals. So 10 to the 5 pascals. And the atmospheric pressure is, we usually just say 1 bar, but if you want to be more specific, 1.013 follows. And yeah, and so just to recap this, both lift and drag, they come from the same idea, and they both are about how fast the airflow is, and change in momentum and forces. And that's all. I hope this video helped you to understand. I'm really sorry it's long, but I want to make sure it's helping you understand in the simplest way. Have a lovely day.